Why does entropy generation impact real-world heat engines? Imagine trying to run a car engine that keeps losing some of its fuel as waste heat. That's similar to what happens in real heat engines because of entropy generation. When engines operate, they don't do so perfectly. Every process involves some irreversibility, which means energy gets spread out or lost in ways we can't fully recover. This loss is what we call entropy generation. Entropy is a measure of disorder or randomness in a system. In simple terms, it shows how energy becomes less useful. According to the second law of thermodynamics, entropy tends to increase in natural processes. If an engine could run without any irreversibility, the total entropy change over a cycle would be zero. That's an ideal scenario, and it would mean the engine operates at maximum efficiency, called Carnot efficiency, which depends only on the temperatures of the hot and cold sources. But real engines are never perfect. They face issues like friction, heat transfer across temperature differences, fluid viscosity, and unrestrained expansions. These are all sources of irreversibility. As a result, entropy is generated inside the engine cycle. Instead of staying the same, the total entropy increases, meaning some energy is lost as waste heat or dissipated in other ways. This entropy generation has a big impact. First, it reduces efficiency because some of the input energy is no longer available to do useful work. It's lost as heat that escapes into the surroundings. Second, it degrades the quality of energy, turning high-grade thermal energy into lower-grade heat that can't be converted into work easily. Third, it sets a fundamental limit on how well a heat engine can perform. No matter how well you design it, some irreversibility will always occur, preventing it from reaching the ideal Carnot efficiency. Engineers use measures of entropy generation to find where these irreversibilities happen. By understanding where energy is being wasted, they can make improvements. For example, better insulation, smoother fluid flow, or more efficient heat transfer methods can help reduce entropy production. This means engines like internal combustion engines, gas turbines, and steam turbines can become more efficient, use less fuel, and produce fewer emissions. In the end, entropy generation is a key factor in real-world heat engines because it explains why they can never be perfectly efficient. It also guides engineers in designing better systems that waste less energy and operate more sustainably. Managing and reducing entropy production helps make our engines more effective, saving resources and protecting the environment.